let's play around with some of these scalars that we obtained by doing something like PA, VA, right? We know that that's a scalar. So let's say that we have a particle and it has a momentum PA. So here is the momentum of a particle PA. Or rather particle for momentum. And this velocity for vector is the velocity of some observer. So we're going to get a number, an invariant quantity, as a result of this operation. So particle for momentum, observer for velocity, and we can evaluate that. So of course P lowered comes from this, as we know. So we're going to use the metric. So we'll have a P B VA, and that is G00, P0 V0 plus G11, P1 V1 plus G. All the cross terms are in the metric are 0. P2 V2 plus G33 P3 V3. But let's say that the observer, so the for velocity of the observer, so the observer is stationary, so the observer doesn't have has 0 values of V1, V2, V3, so this could be X, Y, and Z. And so this becomes, so if V1 equals V2 equals V3 equals 0, so this is a particular observer, then PA VA becomes just G00, P0 V0, and the metric term is -1. Notice, by the way, that we now are using, right, so we're using GAB equals -1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So when we first started and we were thinking of two vectors, we actually had the time and space. The minus sign was with the space part. So that doesn't change the physics. But the important thing is that space and time come in with opposite signs. So now we flip them, but that doesn't change any of the physics. So we have a minus sign here, and right, V naught is just 1, and so we get minus P naught, and that's just the 0th component of the form momentum of the particle, which we know to be the energy, as we've seen before. And so we can say that the energy of the particle is minus PA VA. This is a scalar quantity. We evaluated it for one particular observer, an observer that is, well, all observers, so we can generalize this for all observers, but the point is that we made it easy for ourselves to evaluate it using a specific observer whose for velocity has these components equal to 0. So the momentum of this observer is 0. All observers, even if they don't have this, are at the location of the particle, and this is the so this is the energy of the particle. They are measuring. This is the energy of the particle as measured by these observers who are at the location of the particle, and our observers just sitting at the location of the particle. Other observers can be moving in different ways, and the particle has its own momentum, right, as we see there. So what is the energy of the particle? Well, we already found this. That's PA, and that was minus E squared plus P squared plus momentum squared, and that was equal to minus M squared. Right, we found that earlier. Again, we had the signs flipped for a metric, but this gives us that the energy of the particle is M squared plus P squared. And if you recall, of course, there are factors of C here, and we evaluated this at low speeds and found that it was equal to the rest mass plus the kinetic energy. But the point here is that all observers measure the energy of the particle to be this quantity.